Good morning, I'm Manuel Zarzo, and in this Unit 5 Inference, continuing with the topic of distributions in sampling, I will talk about distribution of the sample variance. Good. This is the formula for the sample variance that we use in statistics very often. So it's every value minus the sample mean squared. We sum for all of the values, and then we divide by n minus 1. So this is some kind of striking or interesting that it's nearly an average, because we sum, so if we have a sum divided by n, that would be exactly an average, but it's not exactly the average, it's divided by n minus 1. So this is some kind of curious that we explain in the first units of statistics. But now, today in this video, I'm going to explain the reason. Why? Why do we divide by n minus 1? Well, the mathematical expectation of this sample variance with this formula, I mean dividing by n minus 1, okay, it can be demonstrated mathematically that this is exactly this sample variance. But, okay, it's an unbiased estimator. Okay. But if we divide by n, this is what I'm representing here as a subindex, so this sample variance computed divided by n instead of n minus 1, the formula, the mathematical expectation is n minus 1 divided by n multiplied by the sample variance. So it means that it is an asymptotically unbiased estimator. So if n is big, for example 100, so that would be 99 divided by 100, which is nearly 1. So actually the bias tends to 0. But if the sample size is small, like for example 4, so we just take 4 values, so it's 4 minus 1 is 3, so 3/4. So we have a bias which can be not negligible, I mean, so more or less important bias. So the formula, the rule that we have obtained is that the average of the sample variance is the population variance, but with the condition that we apply this formula, the formula divided by n minus 1. Okay, and then the variance of this sample variance is this, okay, and then when n tends to infinite, this variance tends to 0. And this is the definition that I provided in a previous video about a consistent estimator. Okay, and then what I'm going to do next is a demonstration with star graphics of this formula. Okay, so now what I'm going to present in the next slide is 10,000 samples of size n equal 4 that are taken from a population with an average of 10 and the standard deviation equal 2. Okay, so I have simulated this data with the star graphics, and then so if we apply this theoretically, so the mathematical expectation of the sample variance is sigma squared, which would be 4. But if we compute the sample variance dividing by n, so based on this formula, we should get a value of 3. So now we're going to check if this is actually what we get by simulation. Now, so 10,000 samples, data from star graphics. So I have here 10,000 rows. In every row here, I have 4 values. Okay, so every row corresponds like a sample, a random sample taken from the population. I have simulated these values so that the average is 10 and the standard deviation is 2, and they are normal distribution. So now for every row, I compute this sample mean, and then I compute this sample variance but dividing by n, and then I compute this sample variance but dividing by n minus 1. Okay, well, this is actually the values that we use in this subject of statistics. Okay, well, so next what I do is to compute the column averages. Okay, so the column average is the following. This is 9.997, so this is nearly 10, which actually makes sense because the population has an average of 10. Okay, so the average obtained experimentally is nearly 10, which is the value of the population. So this simulation is correct. Okay, and then if I compute the average of this column, the average is 3.011. Okay, so and the theory was telling me that the value should be 3. So we are getting nearly a value that is very close to 3, which makes sense. So the theory agrees with our simulated data. But if I compute the average of this column, the value that I get is 4.01, which is interesting because the theory tells that the expectation of the sample variance computed by dividing by n-1 is exactly 4, and this is nearly the value that I have. Okay, so using this simulation of 10,000 samples agrees with the theory. So why is it the reason that when in statistics, when we compute this sample variance, we always divide by n-1? This is somewhat strange. Why is that the reason? Because the bias is 0. So then let's continue with these 3 columns. If I make a histogram with these values, okay, this is what I get. So I'm getting a normal distribution, which makes sense because data come from a normal distribution. Okay, but what happens if I make a histogram with these values of the sample variance? But this is the histogram that I obtained. The histogram is not normal. This is very important. Okay, this is a special distribution that we need to explain in these units of inference. This will be called the chi-squared distribution. Okay, this distribution is positively skewed, and this distribution is needed for inference. And this is interesting, okay, because here we have a lot of samples. So if I compute the sample variance of the samples, and then I make a histogram, the histogram is positively skewed, follows a very specific type of distribution. That distribution is called chi-square. I will explain this in a further video. Okay, so then what happens if I have a population of individuals that follow a normal distribution with an average m and the standard deviation sigma that are unknown? Okay, so I take SRS, simple random sampling. This is the first sample, the second sample, and so on for a lot of samples. Okay, then from every sample I compute the average, and then I compute the variance. This is the population of all possible samples that I can take. Well, then if I make a histogram, or if I study the distribution, in this case, as the average is normal, as the variable that I'm measuring is normal, okay, the sample average will be normal for any kind of sample size. And then if I increase the sample size, the variability will be smaller. Okay, so the sample mean will follow a normal distribution for any kind of value n, and then, as I explained in the previous video, the average will be m, and the standard deviation will be sigma divided by the square root of n. And then we have this formula, the chi-square distribution, as I explained in the previous slide. Okay, so if we make this operation, okay, so if we take that column of values of sample variances, okay, the values of the sample variances for the different samples, and then we multiply by the constant n-1, and then we divide by the constant sigma squared, so that column of values will follow a chi-square distribution. A chi-square distribution with n-1 degrees of freedom. So this is a new concept, the concept of degrees of freedom, that is something new that I will explain in another video. Okay, but this is true only if x is normal. So important. This distribution of the chi-square only is true in the inference from normal distributions. Okay, so here I finished this video about distribution of the sample variance.